All right, let's tackle one of the absolute biggest challenges in AI today. How do we build models that are genuinely smart and not just, amazing at memorizing things? It's really the difference between true understanding and just being a super advanced parrot. So let's dive into how we can teach an AI to actually learn. This right here is the million-dollar question. When we're training a model on a ton of data, how do we make sure it's picking up on the real underlying patterns so that it can handle totally new situations it's never encountered before? In other words, how do we get it to generalize?
The first major roadblock on this whole journey is just avoiding what we call the memorization trap. This is what happens when a model gets so good at its training material that it becomes completely useless for anything else. Now, this trap has a technical name, overfitting. But honestly, the best way to think about it is like a student who crams for a test. They've memorized the exact answers to every single practice question. They might ace that practice test, right? But the second the final exam asks the same concepts in a slightly different way, they're totally lost. The model hasn't learned the ideas. It's just learned the noise.
Yeah, this slide just breaks it down perfectly. A memorizing model, one that overfits, is an absolute master of the data it's already seen. It might notice that, just by chance, every single picture of a cat in its training data has a green background. So it incorrectly learns that a green background is part of what makes something a cat. But a generalizing model, it's smart enough to ignore that fluke. It focuses on the real stuff, the whiskers, the pointy ears, and so on.
So if models can fall into this trap so easily, how do we actually test them? How do we give them a proper final exam to see if they've actually learned anything, or if they've just been cramming this whole time? Well, the solution is actually pretty clever. We split our data into 3 different piles. First, you've got the training set. That's the homework. It's where the model does all of its learning. Then you've got the validation set. Think of this like a practice quiz. We use it to check in, tune the model's settings a little, and just generally see if it's on the right track. And finally, the test set. This is the final exam. It's brand new data the model has never, ever seen, and it gives us the final, honest-to-goodness grade on how well it's going to do in the real world.
And here is the golden rule, the one rule you absolutely cannot break. You cannot cheat. Like the slide says, you only get to use the test set one time. If you let the model peek at it during training or even use it to tweak the settings, you've contaminated the exam. It's exactly like giving a student the answer key before the test. Their score becomes totally meaningless. That test set has to stay in a locked box until the very, very end.
So this brings us to this fundamental tension in machine learning, something I like to call the Goldilocks problem. We are constantly searching for a model that is just right, not too simple, and definitely not too complex.
See, on one side, you've got a model with high bias, which is called underfitting. It's just too simple. Imagine trying to describe a beautiful, complex curve using just a straight ruler. It's going to miss all the important details. Then, on the other extreme, you have high variance, or overfitting. This model is way too complex. It's like a wildly squiggly line that twists and turns to hit every single data point perfectly. It's not fitting to the signal anymore, it's fitting to the noise.
And this graph shows that balancing act perfectly. As we make our model more and more complex, look at the blue line, the training error. It just keeps going down. I mean, of course it does. The model has more power to memorize everything. But now, look at the red line, the test error. It goes down at first, which is great. The model is learning the real patterns. But then it hits this sweet spot, this minimum, and it starts to climb back up again. That's the point where it starts overfitting. Our entire job is to find the very bottom of that U-shaped curve. This whole balancing act, this fundamental challenge, is what's known as the Bias-Variance Tradeoff. It's this constant struggle to build a model that's smart enough to learn what's real, that's low bias, but also disciplined enough to ignore what's just random chance, that's low variance.
Okay, so we understand the problem. And the good news is we are not helpless against overfitting. Data scientists have a whole toolkit full of strategies to fight back and help our models generalize.
Here's some of the heavy hitters in that toolkit. We can just straight up reduce the model's capacity, make it simpler. We can use something called regularization, which is kind of like putting a tax on complexity to force the model to be more efficient. We can use a really cool technique called early stopping. And we can build ensembles, which is basically like asking a whole committee of models for their opinion to get a more robust answer.
Let's just zoom in on early stopping for a second, because it's so intuitive and clever. As our model is training, we watch the training error go down, which is what we want. But at the same time, we're also watching the validation error, our practice quit score. The moment that validation error stops getting better and starts to creep back up, we hit the brakes. We stop the training right there, at that sweet spot, before the model even gets a chance to go off the rails and start memorizing noise.
Now, all these techniques are great for preventing a model from going bad. But what if we could design a model that actively looks for the most generalizable solution right from the very start?
To get this idea, we need to talk about something called a margin. In a classification problem, the margin is basically the safety buffer. It's the empty space between the line you draw to separate two groups of things and the closest data points on either side of that line. And this brings us to an amazing algorithm called the support vector machine, or SVM. An SVM doesn't just find any old line that separates two classes. It specifically hunts for the one line that makes that margin, that empty road between the two groups, as wide as it can possibly be. By maximizing this safety buffer, it finds the most robust, the most stable, and by its very design, the most generalizable solution. It's pretty genius.
So let's pull back from the theory for a minute and get practical. Why does all of this stuff, the trade-offs, the testing, the toolkits, why does it matter so much out there in the real world?
Well, let's take a really common algorithm, like logistic regression. It's used everywhere to make critical binary decisions, yes or no, true or false. A bank might use it to predict the probability that a loan should be approved. Now, for that prediction to be trustworthy, especially for a brand new applicant the bank has never seen, the model has to be able to generalize from past data, not just have it all memorized.
The stakes are just incredibly high across the board. Think about fraud detection. A model that only memorizes old fraud schemes is going to completely miss new ones. Or in medicine, a model that overfits to patients from one hospital might fail spectacularly on patients from a different background. Or even in business, predicting which customers might leave a service requires understanding the real reasons why, not just the random quirks you saw in last month's data. So at the end of the day, generalization isn't just a technical problem, it's almost a philosophical one. As we build these incredibly powerful AI systems, the real challenge is making sure they're learning the fundamental rules of our world, not just the noisy, messy examples we happen to show them. It's all about preparing them for a future that is, by its very nature, something they've never seen before. Thanks for tuning in.